Hi guys, how are you? Today we're going to start with a new unit. It's unit 10, logarithms and logarithmic functions. So as usually, I'm going to present my screen and I'm going to start talking to you about why this function, this thing, this topic called logarithms is so important in math and why we need it. Okay. So first of all, I'm going to start with a sample word problem for you guys to understand why we need logarithms. Okay, so let me start with this, and what I'm going to say is that in a specific place or at a specific place there's a population of 1000 rabbits. Okay, and this population is growing, or this population is duplicating each year. Okay, so population is duplicating each year. Okay, so in this situation, as you know, or as you might guess, if we want to write a formula, we want to write a function, an exponential function to model this situation, we would say this is 1000 times 2 raised to the power of x. Okay, usually, as you already know, we would use, instead of x, we would use t, because t stands for time, so it's more intuitive. Okay, but it's the same as using x. But actually, we have this exponential function which is telling us the population as at each specific moment in time. Okay, population of rabbits is duplicating each year. Okay, so now let's say, for example, how many, or no, let's say usually like the kind of question you got in the previous unit about exponential function. How many rabbits are there after, how many rabbits will there be after 2 years? Okay, easy, you know how to do this one, right? So in this case, what you would do is saying, okay, so the value of time is 2, so I replace t with a 2, so here I have 1000 times 2 squared, which is 4, so this is going to be 4000. So after 2 years, I have 4000 rabbits. Okay, so now we can ask another question here. The other question is, how long will it take until there are 8000 rabbits? How long will it take until there are 8000 rabbits? Okay, so in this case, what we do this, now my 8000 is here, so I want to find the value of t, for which f of t is going to be 8000. This one is easy because the only thing I have to do is isolate the variable. So what I'm going to do is making 8000 divided by 1000, right? And all of this is going to be 2 raised to the power of t, right? So 8000 divided by 1000, you know it's 8, so 8 equals 2 raised to the power of t. And we know that 8 is the same as 2 raised to the third power. So actually this is going to be 8 equals 2, 2, which means that t equals 3. Okay, this means that it takes 3 years for the rabbits to be 8,000, for the population of rabbits to grow up to 8,000 rabbits. Okay, this one was easy because we know that 2 cube equals 8, okay? But what happens if I ask you how long will it take until there are 50,000 rabbits? Okay, in this case, I can copy this part. In this case, I'm going to say 50,000 equals 1,000. Okay, in this case, I will say 1,000 equals 1,000 times 2 raised to the power of t. Then I isolate this expression, so I will get 50,000 divided by 1,000 equals 2 raised to the power of t, which gives me 50 equals 2 raised to the power of t. What happens here? Here my problem is that I know that 2 to the power of 5 is 32. I also know that 2 to the power of 6 is 64. I don't know how to get something in the middle, okay? Something accurate in the middle. I don't know yet how to solve that, okay? So, guys, we need something to get to that point, okay? So, here's where the logarithm comes, okay? So, the logarithm, let me write definition here, and then I will solve this problem, okay? So the definition of the logarithm, I'm going to write it in terms of a formula, okay? Because I think it's more intuitive like that. It's more intuitive that way. So this is a bit weird the way I'm going to write it, but you will understand it in the end. If we have an equality like that, a equals b raised to the power of c. Imagine those are numbers like these ones, okay? Just a number a equals another number b raised to the power of c. If this happens, this is equivalent. Let me find the double arrow here. Okay, if this happens, this is equivalent to c equals logarithm. Let me find out how to write it here. Logarithm base t of a. Okay, that could be considered as the definition of the, or as the generating formula or the relationship of a logarithm. If we want to express that in words, it would be something like this. The logarithm base, or actually we would say the logarithm base b of a logarithm base b a, dicho en español, el logaritmo base b de a, the logarithm base b of a is the number to which I need to raise B in order to get A. Let me explain this in a minute. Logarithm base B of A is the number to which I need to raise B in order to get A. Lo digo en español. El logaritmo base B de A es el número al que tengo que elevar B para obtener A. Okay, let me solve an example here. Let's rewrite this relationship with known numbers. Okay, let's use this relationship here, okay? 8 equals 2 raised, or this actually. 8 equals 2 raised to the third power, okay? So in that case, what we're going to say is that 8, I'm rewriting this over here, okay? 8 equals 2 raised to the third power, right? So this is equivalent to saying that, sorry, I missed something here, equals C, okay? The logarithm base B of A is the number to which I need to raise B in order to get A. Okay, this, sorry, I had already written that. Okay, it was here, perfect. Okay, so 8 equals 2 raised to the third power, right? Then this means that the number to which I need to raise B in order to get A is C. So let me write this down. So 3 is the logarithm base 2 of 8. Okay? The logarithm base 2 of 8 is 3. Why? Because 3 is the exponent I need to put on the 2 in order to get 8. Okay? I know it's a bit confusing right now. Let me finish. Let me, sorry guys. Let me solve a couple of examples more so you get more familiar with this concept, okay? So let's say, for example, let's take a couple of examples from the book. Let's say, for instance, numbers you guys know. 27, you know, it's 3 raised to the third power. Sorry. 3 raised to the third power, right? Then 3 is the number which I need to raise 3 in order to get 27. Okay, so the logarithm base 3 of 27 is 3. Okay, another example. Another example would be, sorry. Another example could be using powers of 10, okay, which are also quite intuitive. So, for example, 1000. 1000 is the same as saying 10 raised to the third power, right? Which means that 3 is the logarithm base 10 of 1000. Okay? That's the relationship. Okay? This is the relationship that let us know that we do need logarithms. Okay? So let's solve this example here and then I will go back to the definition. Okay, great. So what I need here is this, right? I'm asked about the value of this t, right? So let me take this and let me write it down here. Okay, have that 50 equals 2 raised to the power of t. So this implies that t equals the logarithm base 2 of 50. Okay, I need to find this t is the exponent. I need for this 2 in order to get 50. Of course, it's not going to be a whole number, it's going to be a decimal number. It will be, if we had that 2 raised to the power of 5 is 32 and 2 to the power of 6 is 64, it's going to be 5 point something, 5.5 or 5 point something. Okay, we need to use our calculator to find this. Okay, you cannot do this just like that. You need your calculator. Okay, so let me use the Google calculator, which is quite useful in this case, and you will see it's very easy to introduce logarithms in the Google calculator. Okay, using just the browser. Okay, so the only thing I'm going to write is logarithm base 2 of 50, and Google answers this. Okay, so it's 5.64. This is equals 5.64, which means that 2 raised to the power of 5.64 is going to give me 50. And in my specific problem, sorry, means that it will take 5.64 years, so more or less like 5 years and 7 months for the population of rabbits to grow up to 50,000. Okay, that's the meaning of this, right? Okay, so now that we know this, let's go back to this definition. Let's solve a couple more of examples here. And in the next video, we'll talk to you about the properties of the logarithms. Okay, so let's finish with the definition. So once again, this is the relationship. If there's this equality A equals B raised to the power of C, this implies, okay, it's a co-implication. One implies each other, one implies the other. So it implies that C equals the logarithm base B of A. And there are a couple of conditions here. Same as with the exponential functions, here we need to say that always B has to be larger than 0. Okay, let me change this, insert equation. So always B has to be larger than 0. B also has to be different from 1. Okay, these two conditions, we already had them in the exponential function. Actually, if you think about it, I'm talking about this base. As in the exponential function, the base of the in the logarithm, this base cannot be negative. Okay, it has to be positive. Okay, this comes as a consequence of the logarithm being the opposite or the inverse function of the exponential. Okay, so this comes from the exponential function. So b has to be positive, b has to be different from 1, because you know that if we raise 1 to any power, it remains 1, remains being 1. So There's no sense in using 1 as the base of an exponential function. Okay, so b has to be positive, b has to be different from 1, and here is the new condition. There's another one that we didn't have before, and it's that a also has to be larger than 0. Why? Because if a is negative, it means that we're going to get complex numbers. And as I said, with exponential functions, we don't want complex numbers. Okay, so let's remember this for the logarithm. The base has to be positive, the base has to be different from 1, and a has to be positive as well. Okay, let me solve a couple of examples more here because I used some positive, really straightforward examples, and I want to solve a couple of more not that intuitive examples. Okay, so let's insert here this again. Okay, so for instance, let's say 0.01. 0.01 is the same as saying 10 raised to the power of minus 2. Okay, so this means that minus 2 equals the logarithm base 10 of 0.01. Okay, so the logarithm can be negative, of course. It means that we are finding the exponent that gives me a number smaller than 1. Okay, so you know negative exponents means this means that they are inverted, so you will get a number below 1. So that's when you get a number, a negative number here. Okay, same thing with, let's do another example. So same thing here with, I don't know, let's use fraction. So 1 divided by 27. Okay, 1 divided by 27 is the same as saying 3 raised to the power of minus 3, right? So this implies that minus 3 equals the logarithm base 3 of 1 over 27. Okay, so that's it. And last thing I want to tell you guys about this is after I said the definition of logarithm, I want to tell you the most common basis for logarithms. Okay, there are 3 bases which are very, very common. Okay, actually 2. The most common ones are 2, but let's write them down here. That's the, let me make sure of the names here in your book. I don't want to, okay. We have, you might guess, one of the most common ones is the logarithm base 10, okay? So that's called actually common logarithm. Common logarithm base 10. Okay, so common logarithm is this, the logarithm base 10 of x, okay, of any number. And the other one, which is very, very common, is the natural logarithm, which is, guess, this new number I introduced to you guys this previous unit, which is p. Okay, the mathematical constant p, which as I already said, and you guys know, it's equals more or less 2.70 something, is the other one, which is so common in logarithms that it even has a name for it. So natural logarithm means logarithm base p. So this is a logarithm base p of, actually, it's not the way we write it, okay? We write this like this. We don't need to write the base. Actually, I'm going to erase this because you're not going to find that in any math book, you're going to in your calculator, and nowhere. You're going to find this expression, right? The natural logarithm of a number. Okay, actually here in the Google calculator, you're going to find that. Natural logarithm of 1. Okay, natural logarithm of 1 is 0, right? Because any number raised to the power of 0 gives you 1. But this is just for you guys to know that these are the two most common basis for logarithms. Okay guys, thanks for watching. This is everything for this video, and in the next video we'll tell you about the properties of logarithms.